Calculus 1 video lecture number 6 on limits at infinity and horizontal asymptotes. So we're going to start off by considering the function f of x equals tan inverse of x. You should have this graph burned in your brain. So we know that this function has two horizontal asymptotes, one at pi halves and one at negative pi halves. And it also goes through the origin at 0, 0, and it's increasing. So now we're going to consider limits at infinity, meaning the limit as x approaches positive infinity. So imagine you're walking on the graph going towards positive infinity. Tan inverse of x, the function approaches what y value? Well, it approaches pi over 2. That's the horizontal asymptote in the positive x direction. And similarly, if we look at the limit as x approaches negative infinity, so imagine you're walking on the graph, but this time you're going in the negative x direction. Now, tan inverse of x, or the function, is approaching negative pi halves. And we know that it never actually achieves the values of pi halves or negative pi halves, right? It's never actually going to equal those values, but that's what it's tending towards, and those are the equations of the horizontal asymptotes. So notice that the equations of the horizontal asymptotes are precisely what the limit of the function is as x approaches positive infinity and negative infinity respectively. So this is the definition that we have now for a horizontal asymptote. The line y equals L is a horizontal asymptote of y equals f of x if the limit as x approaches positive infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. Now you might remember some methods that you learned in precalculus for finding horizontal asymptotes for rational functions dealing with the degree of the numerator and denominator, and that's a great way that you can check your work. But now that we're in calculus, we're going to use this limit definition anytime we're asked to find horizontal asymptotes. Now let's look at this graph here. We don't have an equation to work with specifically just yet, but I have a function g of x, and the graph is shown here in pink. So we're going to find the following. Part A, we want to find the limit as x approaches positive infinity of g of x. So imagine you're walking on the graph, headed in the positive x direction forever and ever. What y value or what function value is g of x tending toward? Well, it's oscillating, but it does seem to level out. And it seems like x is approaching, as x approaches positive infinity, g of x approaches 2. Now, what about the other direction? What if x approaches negative infinity? So now we're walking on the graph. We're headed in the negative x direction. What y value are we approaching? It looks like -1. All right, part C, the limit of g of x as x approaches 2. So here's 2 on the graph. I need to consider the limit from the left-hand side and the right-hand side separately. So let's go ahead and do that. So the limit as x approaches 2 from the right of g of x, let's see. So I'm approaching 2 from the right side from values larger than 2. Notice the graph is increasing without bound. So that limit is positive infinity. And then the limit as x approaches 2 from the left of g of x, let's see what's going on. So we're coming from the left side of 2 or from values smaller than 2, and now the graph is decreasing without bound. The graph or the function values are approaching negative infinity. Well, what does this tell us? The limit from the left of 2 is negative infinity, whereas the limit from the right of 2 is positive infinity. Well, when the limit from the left does not equal the limit from the right, that means the limit does not exist. And don't put equals. It just does not exist. It doesn't equal anything. That's what that means. Lovely. Now let's look. The limit as x approaches 0 of g of x. So again, we're approaching 0. Let me consider the limit from the left and the limit from the right. Well, in this case, I can see that they're both approaching negative infinity. The limit from the left equals the limit from the right. Let's write that out. the limit as x approaches 0 from the left of g of x is equal to negative infinity, which is also the limit as x approaches 0 from the right. So I can say this is equal to negative infinity. And then lastly, the limit as x approaches negative 2 from the right. So where's negative 2? Negative 2 is right here. We're approaching from the right side, so from values larger than negative 2 this way. Okay, what y value does it seem to be approaching? That looks like it's almost negative 1/2, but not quite, so I'll say negative 0.4. Just eyeball it. Looks good. Last thing, we need to give the equations of the asymptotes, so that would be horizontal and vertical. So let's see, what do we have here? Well, I know right away my horizontal asymptotes come from the first two limits that we took, the limit to positive infinity and negative infinity. So those equations are going to be y equals 2 and y equals negative 1. And then what about vertical asymptotes? Did we have any? Certainly, we have one here at x equals 0, right? Remember that limit came out to be negative infinity. And we have another one here at x equals positive 2. Very nice. So that completes that problem. You'll have a few exercises similar to this in your homework where you're just given the graph. You're not going to be given the equation that it represents, and then you'll have to use it to find some limits and asymptotes. Now we're going to consider our good friend, the reciprocal function, f of x equals 1 over x. Do you remember this guy? So let's graph it, and then we're going to use the graph to find the following two limits. The limit as x approaches positive infinity for 1 over x, and again the limit as x approaches negative infinity for 1 over x. So reciprocal function has vertical and horizontal asymptotes at the x and y axes. Probably remember learning this in pre-calc. And then just a couple key points that are easy to draw on the graph. Usually 1, 1 I use for this portion here that lives in the first quadrant. And then remember, it hugs those asymptotes, it doesn't cross them. And then negative 1 is another good point to plot for the other portion of the graph. Beautiful. All right, now let's use our graph and see if we can evaluate these two limits. So the limit as x approaches positive infinity for 1 over x. So now imagine you're walking on the graph. You're headed in the positive x direction forever and ever. What y value are you tending towards? Where's the graph going? It's going towards 0, towards y equals 0. And similarly, the limit as x approaches negative infinity for 1 over x. Let's see. Now we're walking this way. I'm going to put you upside down, okay? So you don't fall off the graph. Going this way forever and ever. It looks like you're tending towards 0 again. Very good. And you should have been able to kind of reason about this limit even without the graph, because let's think about what's happening. As x approaches infinity, the denominator of this expression is getting really, really large, right? So if you think about it, x is approaching infinity. You have something like 1/10, and then it becomes 1/100th, and then 1/1000th, and then 1 over. So the larger the denominator becomes, the smaller the overall expression becomes. So anytime the denominator blows up or it gets large without bound, the entire expression approaches 0. And so it doesn't necessarily need to be just 1 over x. In fact, 1 over x squared, 1 over x cubed, or 1 over x to the r, for any rational number, the limit as x approaches positive or negative infinity will be 0. Okay, so if you have a constant in the numerator and the denominator is blowing up, then that means the whole expression is getting really, really tiny, and so the limit is equal to 0. All right, so we're going to use that theorem to help us evaluate the following limits. And please pay attention, make sure when you're working on limits that go to infinity that you show every step of the process, just like I'm going to outline here. Don't skip any steps. If you know some shortcut ways and you can mentally check, that's good. You can use that as a check, but if you want full credit on an exam or a quiz or anything, you need to show all the steps that I'm going to demonstrate here. All right, when we're dealing with rational expressions and you're taking limits to infinity, you want to divide by the degree of the denominator. So the degree of the denominator is determined by the highest power of the variable that you see down there. Okay, sometimes it's x, sometimes it's something else. So you're going to divide by the highest power of the variable in the denominator. In this case, the highest power of x that I see in the denominator is to the first. So I'm going to divide numerator and denominator by x. You'll see why in just a second. I want to use the theorem that we just listed. So now here I have the limit as x approaches infinity, and I'm going to divide all of the terms in the expression by x. So 3 divided by x is just, or 3x divided by x is 3, and then I have plus 5 over x. And then in the denominator, x divided by x is 1 minus 4 over x. Good. Now this next step, this one is a little bit extra, and then I want you to understand what's going on. You don't have to write it out for every problem. I'm going to take the limit now and distribute it to each of the terms in the numerator and denominator. So we have the limit as x approaches infinity of 3 plus the limit as x approaches infinity for 5 over x. And then in the denominator, we have the limit as x approaches infinity of 1 minus the limit as x approaches infinity for 4 over x. All right, let's go term by term. So the limit as x approaches infinity of 3, that's just 3. It's a constant. It's not going to change. Fabulous. Plus limit as x approaches infinity of 5 over x. Now, in the theorem on the previous page, we had the limit as x approaches infinity for 1 over x. But it doesn't matter if it's a 1 or a 5 or even a million. If the numerator is a constant, and that constant doesn't change, but the denominator is getting bigger and bigger and bigger, that's still going to dominate or overpower, and the whole expression is going to approach 0. Good. So we have 3 plus 0 in the numerator. Now let's look at the denominator. So we have the limit as x approaches infinity of 1. I don't see any x's in that expression, so that's just going to be 1. Minus the limit as x approaches infinity of 4 over x. Same thing, the denominator is getting larger and larger and larger. 4 is just a constant, it's not changing. So this whole term goes to 0 as well. And we're pretty much done. So in the numerator we have 3, in the denominator we have 1, so this limit is equal to 3. And that also is the equation of the horizontal asymptote, if we were to try to graph this function. Now, as I mentioned earlier, you might remember from precalculus that when you're finding equations of horizontal asymptotes, if the degree of the numerator is equal to the degree of the denominator, all you need to do is take the ratio of the leading coefficients, in this case 3 divided by 1, and that gives you the equation of the horizontal asymptote, which is 3. But that was cool to do in pre-calculus, and now that we are in calculus, we justify this procedure or process by taking a limit. However, use the pre-calc way to check that you actually did the limit correctly. That's fine. Lovely. Let's look at another example. So here we have the limit as t approaches negative infinity of t squared plus 2 over t cubed plus t squared minus 1. All right, remember we need to divide by the degree of the denominator. So the highest power of t that I see in the denominator this time is t cubed. So I'm going to divide numerator and denominator by t cubed. And I have here the limit as t approaches negative infinity. T squared divided by t cubed, that's going to be 1 over t plus, I have 2 over t cubed here. And then in the denominator, t cubed over t cubed is 1 plus, this is going to be 1 over t minus 1 over t cubed. Now let's go take the limit term by term. So as t approaches negative infinity, remember, if the denominator gets really, really large, either in the positive or negative direction, and the numerator is a constant, this whole term is going to approach 0. It doesn't matter that it's going to negative infinity. 1 divided by negative a million is very small. It's just negative instead of being positive like in the previous problem, but it's still going to 0. All right, 2 over t cubed, that's also going to 0, just faster. 1 is a constant, so that's staying 1. 1 over t goes to 0, and 1 over t cubed also goes to 0. So what are we left with in this limit? Well, in the numerator, all I have is 0, and then in the denominator, I have 1. And 0 divided by 1 is 0. So we're done. Could we use our pre-calc methods to confirm? Well, do you remember from pre-calculus, if the degree of the denominator is higher than the degree of the numerator, then automatically the equation of the horizontal asymptote is y equals 0. And we confirm that right here. Our limit was 0, which would be the equation of the horizontal asymptote. Basically, the denominator is growing faster than the numerator, so the overall limit's going to be 0 for the expression. Good, good. The only difference notice here with my work compared to the last one is I didn't write lim in front of each term. You don't have to do that, okay? But you do need to show dividing out by the highest power of the variable in the denominator. You need to show all of those limits that go to 0 and then your result, and make sure you write lim as long as you still have variables in that limit. Okay? Very good. Let's consider some more examples that are going to be a little nuanced, so you have to be careful here. We have the limit as x approaches positive infinity of x plus 2 over the square root of 9x squared plus 1. Now, I want you to be careful because do you notice in the denominator how we have the square root of 9x squared plus 1? So what is the degree of the denominator? What is the highest power of x that I need to divide by? Well, it's the square root of x squared, and that is a highly sensitive little creature that we have to deal with. If you'll recall, the square root of x squared is equal to the absolute value of x, right? It's not just equal to x. You can't assume that x is non-negative. And absolute value of x, we have defined piecewise as x if x is greater than or equal to 0, and negative x, or the opposite of x, if x is less than 0. So we need to be careful here, because when I divide out by the highest power of x in the denominator, in this case I'm going to divide by the absolute value of x. Now I have to decide which piece of the piecewise function applies in this limit. So what you need to do is look at which way x is going. X is going towards positive infinity. So I'm headed in the positive x direction, which means absolute value of x is defined to be x. So I'm going to use the positive portion of my piecewise defined function because this limit x is going to positive infinity. I'll show you what you would do if it was going the other way in another example. But you do need to show that you thought about it. All right, now let's go ahead and divide by the absolute value of x, and that might be a little bit tricky to do in the denominator. So we have the limit as x approaches infinity. Remember, we're just using positive x here in the numerator. So I have 1 plus 2 divided by x. And then what do we do in that denominator? Oh my goodness. So here we go. We'll do this off to the side. So I need to divide rad 9x squared plus 1 by the absolute value of x. So I need to divide rad 9x squared plus 1 by rad x squared. Okay, so you're taking radical 9x squared plus 1 and dividing by x squared. So what does this become? Radical 9 plus 1 over x squared. Okay, so now let's plop that down here in the denominator. I have rad 9 plus 1 over x squared. And then now we can go ahead and take our limit. So as x approaches infinity, 1 is 1. 2 over x, that approaches 0. 9 is a constant, and 1 over x squared, that's going to approach 0. So now I'm done taking the limit. Let's see, what's left in the numerator? I have just a 1. And then in the denominator, I have square root of 9 plus 0, which is 3. So this limit is 1/3. Okay, these are tricky to work with, especially at first. So just take your time and make sure you practice enough examples. Feel free to do extra homework problems. Do some evens. Okay, here we go. Example 4, we have the limit as x approaches negative infinity. I have square root of 9x to the 6th minus x over x cubed plus 1. So you might not be too nervous at first. You go, okay, the degree of the denominator is 3, so I'm going to divide by x cubed. But notice in the numerator again, I have radical x to the 6th. And how does that simplify? That's the absolute value of x cubed. Why do I need the absolute value? Because I don't know if x represents a positive or a negative number. I'll tell you when you don't need the absolute value. This is probably running through your brain. If you have the square root of x to the 4th, you don't need absolute value on x squared because x squared is going to be positive anyways, so you don't put them. Same thing, if you had square root of x to the 8th, that would come out to be x to the 4th. If you raise something to an even exponent, you don't need to put absolute value bars on it after, right? The problem is when you take the square root of x to the 6th, or like we did in the previous one, when you take the square root of x squared, it comes out to be x to the 1st. Well, if it's raised to an odd power, it could be positive or negative, and I don't know which way we're going just yet, what x represents, so you need the absolute value bars around it. Okay, so just check. If this exponent is odd, then we need them. If this was even to start with. Okay, so again, we can rewrite this piecewise as positive x cubed if x is greater than or equal to 0, or negative x cubed if x is less than 0. We'll check which way x is going in the limit to decide which part of the piecewise function are we working with. So x is approaching negative infinity. That means I'm working with values for x less than 0 in the limit. So I'm going to use negative x cubed. So how do we deal with that in the limit? As follows. So since the limit, I'm going to summarize right now, is going to negative infinity, all we need to do is put a negative sign or a minus sign in front of the even root. Okay, so what's that going to look like? Allow me to show you. So we have the limit as x approaches negative infinity. Where's the even root? It's right here. You're just going to put that extra negative sign since we're working with the negative portion for how absolute value of x cubed is piecewise defined. And then you have radical. And then you just move on with your life. Okay, so now we're going to divide by x cubed. Remember, when I put x cubed underneath the radical, though, it becomes x to the 6th. So if you need a little help here, you have radical 9x to the 6th minus x, and then you're dividing that by x cubed. So when you put it underneath the radical, now you're going to have 9x to the 6th minus x over x to the 6th. Okay, so in the numerator now we're going to have 9 minus 1 over x to the 5th, and then over x cubed divided by x cubed is 1 plus 1 over x cubed. Okay, finally, it's time to take the limit. So 9 is a constant, 1 over x to the 5th, that's going to approach 0. 1 is a constant, and then 1 over x cubed, that also goes to 0. So what are we left with? I've got a negative, I've got a rad 9, and a 1. Those are the only survivors. I'll write it out again. So we've got negative 9 minus 0 over 1 plus 0. So this is going to be negative 3. Okay, don't feel badly if you're highly uncomfortable from this process. It's new, most likely. So just take your time, rewatch some parts that you need to see explained again, and just keep practicing. Okay, last example before we change gears. We have the limit as x approaches positive infinity. Look, no radicals, you can relax a little bit. Of x cubed minus 2x plus 3 over 5 minus x squared, 2x squared. So let's divide by the highest power of x in the denominator. In this case, it's x squared. And let's go ahead and see what's going to happen. So we've got the limit as x approaches infinity. In the numerator, x cubed divided by x squared, that's just x. Minus, this is going to be 2 over x plus 3 over x squared. Over, we have 5 over x squared minus 2 in the denominator. Looks good. Let's go ahead and take that limit now. So as x approaches infinity, x is going to infinity, right? Okay. 2 over x, that's going to approach 0. 3 over x squared, that approaches 0. And 5 over x squared, that approaches 0. So what do I have left over after everything goes to 0? I've got x over negative 2. And x is approaching infinity. And then if I divide that by a negative 2, all it's going to do is make the entire expression negative. If I take half of infinity or something that's blowing up, it's still going to blow up, okay? It's just going to change in the sense that now it's getting very, very large in the negative direction because there's a negative in front of that too. So for the end result, our limit's going to be negative infinity. Good. If there was a plus sign in front of the 2, then it would have just been positive infinity. Very nice. Now we're going to look at why sometimes our infinite limits come out to be infinity, just like that last problem. So we're going to consider f of x equals x cubed, another good friend of ours. So x cubed, let me plot that here. Some key points, 0, 0. 1, 1, 2, 8 is also a nice one to put. 2, 4, 6, 8. So here's 2, 8. And then negative 1, and then negative 2, negative 8. That'll be over here. And here's x cubed. All right. Now let's use the graph to help us answer this question. What is the limit as x approaches positive infinity of x cubed? So imagine you're walking on the graph, headed in the positive x direction forever and ever. What y value are you approaching? You're not approaching anything. The graph is just blowing up or getting larger without bound. So that limit is positive infinity. Now what if you went the other way? So the limit as x approaches negative infinity. Now you're sliding down the graph. Whee! So as you go forever and ever in the negative x direction, what y value are you approaching? The graph is not leveling off. It's decreasing without bound. So it's approaching negative infinity. And sometimes the term that we use to describe this situation is the end behavior. You might have heard that from Precalculus. So anytime you take an infinite limit, it tells you about the end behavior of a graph. If it has a horizontal asymptote, that's the end behavior. But other times it doesn't have a horizontal asymptote. It either increases or decreases without bound, and that information is also revealed by taking an infinite limit, or a limit as x approaches infinity. Okay, so let's put this all together so that we have a game plan when we're asked to find asymptotes. So if you're asked to find a horizontal asymptote, what do? You're going to take the limit as x approaches positive infinity for f of x, and you have to take the limit as x approaches negative infinity for f of x. Remember, not all functions have the same horizontal asymptote in the positive and negative x directions. Just imagine tan inverse of x. That was one that had two different horizontal asymptotes. So if when you take these limits, if you get a constant, right, not infinity or negative infinity, if you get some constant c, then the equation for the horizontal asymptote is going to be y equals c. If you're asked to find vertical asymptotes, you could take a limit, but all we need to do for our purposes is look at the denominator. So x equals k is going to be the equation of your vertical asymptote whenever x minus k is a factor of the denominator only. Meaning it is not, x minus k is not a factor of the numerator as well. Or your expression has to be in lowest terms in order for you to use this. And we'll look at an example because that's a very delicate situation. Okay, so first example, pretty straightforward. Find the horizontal asymptotes and vertical asymptotes. Now we're in calculus, so this means we're taking limits. So let's start off with the horizontal asymptotes. I'm going to take the limit to positive infinity and negative infinity. So I've got the limit as x approaches infinity of 1 plus x to the fourth over x squared minus x to the fourth. So now I want to divide by the degree of the denominator, so I'm going to divide by x to the fourth. And let's see what we have here. So I have the limit as x approaches positive infinity. In the numerator, I'm going to have 1 over x to the fourth plus 1 over, this is going to be 1 over x squared minus 1. Okay, so now as x approaches infinity, 1 over x to the fourth is going to go to 0. Same for 1 over x squared. And the other two terms are just constant, so they're going to stay the same. And then 1 divided by negative 1 gives me negative 1. All right, now would things have changed? Would my result be different in my limit if x was going towards negative infinity? In this case, I could see no, they would be the same. So I'm not going to write down identical work. I'm just going to address the fact that I thought about it. So we would get the same result as x approaches negative infinity. So that means the equation of my horizontal asymptote is y equals negative 1. Do our precalculus methods confirm this? They sure do. You would divide the coefficients of the leading terms in the numerator and denominator, 1 divided by negative 1. Yep, that's what we got. Okay, what about vertical asymptote? Or asymptotes, you could have more than one. So we've got y equals 1 plus x to the fourth over x squared minus x to the fourth. Now let's factor this completely. The numerator doesn't factor, but the denominator, I can take out an x squared, and I'm left with 1 minus x squared. And that actually factors further into a difference of squares, so I have 1 plus x to the fourth over x squared times 1 plus x times 1 minus x. All right, now let's look at the factors of the denominator. So we've just got x, which is x minus 0, 1 plus x, and 1 minus x. Do you see any of those factors repeated in the numerator? Well, no, the numerator didn't factor at all. So that means the zeros of each of those factors are going to be the equations of my vertical asymptotes. So my vertical asymptotes are at, I have 3 of them. Look at us go. X equals 0 from x squared, x equals negative 1, and x equals positive 1. So we've got 3 vertical asymptotes and 1 horizontal. Very good. All right, bonus example. Are you ready? Yes. So here we go. Same directions. Find the equation of the vertical and horizontal asymptotes. So we've got y equals x cubed minus 6x squared plus 8x over 2x squared minus 3x minus 2. All right, horizontal asymptote. Let's start with that. So I'm going to take the limit as x approaches infinity of x cubed minus 6x squared plus 8x over 2x squared minus 3x minus 2. So dividing by the degree of the denominator, I'm going to divide by x squared. And then we'll be able to take the limit. So I've got the limit as x approaches infinity. In the numerator, I'm going to have x cubed divided by x, so that's x squared, so that's just x, minus 6 plus 8 over x. And then downstairs, what do we got going on? We've got a 2 minus 3 over x minus 2 over x squared. All right, bravo. So x goes to infinity. That means this term's just blowing up, going towards infinity. Negative 6 is a constant. He's going nowhere. 8 over x, that guy goes to 0. And then 2, that's a constant. 3 over x goes to 0. 2 over x squared goes to 0. So let's see. In the numerator, I've got infinity minus 6. That doesn't matter, the minus 6. Eventually, as x is blowing up, minus 6 isn't going to do anything. Divided by 2, it's still blowing up. Which way is it blowing up? Positive or negative direction? Positive. So this limit is going to be positive infinity. Similarly, if we took the limit as x approaches negative infinity, let's think what would be different, right? You would still divide by x squared, simplify everything. It's just at that last step. Let's look at the numerator. This term would be going towards negative infinity divided by 2. The minus 6 does nothing. So that means this limit would be negative infinity. Okay, neither of those are constants though, so that means I don't have any horizontal asymptotes. In fact, notice the degree of the numerator is exactly 1 higher than the degree of the denominator. And that means we have an oblique asymptote. So in fact, how would we find the equation of that oblique or slant asymptote? You would use long division, and you could find the equation of the slant or oblique asymptote. And this is something you should be familiar with from Precalculus. If you're rusty on long division, I'll link up here in the corner a video just going over polynomial long division. Okay, you can't use synthetic for this. Good. So no horizontal asymptotes, okay. All right, that's because there's an oblique. Now, let's look at vertical asymptotes. So vertical asymptotes, I need to have everything fully factored, so let's do that. So we've got y equals, I notice in the numerator I can take an x out, and I'll have x squared minus 6x plus 8 over, denominator factors into 2x plus 1 and x minus 2. Okay, let's keep factoring. I have x times x minus 4 times x minus 2, and then in the denominator 2x plus 1 and x minus 2. All right, so what does this mean for us in terms of vertical asymptotes? Because here we have this repeated factor of x minus 2, and we said vertical asymptotes only happen where the factors of the denominator are 0 as long as they're not also factors in the numerator. So the only unique factor of the denominator is 2x plus 1. So that means my vertical asymptote, I've only got one, is that x equals negative 1/2. Well, you might be wondering what's going on at x equals 2. Because if you look at this graph, right, the function, the domain has two restrictions. The domain is x such that x cannot be 2 or negative 1/2. So what's going on in the graph at 2? Well, remember, we can cancel out this factor, and we actually just have a hole when x is equal to 2. This is a removable discontinuity because we are able to take the limit as x approaches 2 of our graph of f of x, and we'll have x times x minus 4 over 2x plus 1. The x minus 2 is canceled out, and you get 2 times negative 2 over 5, so negative 4/5. So you're going to have a hole or an open circle in your graph at 2, negative 4/5. So here's how I think it to myself. Like both 2 and negative 1/2 are not in the domain, right? We're not allowed to plug in x. However, since x minus 2 is a repeated factor in the numerator and denominator, it cancels out and it's not as dangerous. So you just have a little hole in the graph. You've got that open circle. It's a removable discontinuity. But the ones that can't be canceled out after you factor, those are super dangerous. So those are the ones that are the vertical asymptotes. Okay? And you probably remember doing this a little bit in pre-calc, but without the understanding of limits and continuity and all of what's going on behind the scenes. So that concludes the lesson. There's a lot of material to digest, so just let it marinate. Take your time. And I hope you enjoyed the video. Please give it a thumbs up, subscribe if you haven't already, and we've got more limits and graphing to come. Don't you fret.